All right, I think we're ready. Today we've got a new sensor, a little Hall effect sensor. We're not done with our strain gauge sensor. I'm just giving you a little more time to get it mounted before we go into building the rest of the circuit. Last time we built the Wheatstone bridge for it, but we still need to build an amplifier circuit out of op amps, or a single op amp. So we still need to do that to get a usable measurement out of it. Right now it'll output a really tiny voltage out of the bridge, but it's too small for our Arduino to read, so we need to amplify that. So you got a little bit more time to build the circuit for that, the Wheatstone bridge, and actually mount the strain gauge, so we have that too. This is a really simple sensor right here. It's called a Hall effect sensor, and it's going to detect magnetic field. So we'll talk about that. We're going to do some Mathcad. So we don't usually use Mathcad very often, or at least we haven't. But there's no particular reason. We've just been using Python. But I'm going to do a little bit of the Klein-McClintock process for uncertainty in Mathcad, just because I think it shows it better. We're also going to do a bit of it, not the whole thing, but a bit of it in Python, so that you can see that you can take derivatives in Python using a finite difference method, actually a complex finite difference method, where we use complex numbers with imaginary and real components. And we can do that. And what else will we do? Oh, parameter. We'll estimate a population mean based on a sample mean, and we'll do that with a large sample and a small sample. And I think that's all that we can get through today. Not even sure that we'll get through all of that, but we'll try to. Let's look at the Hall effect sensor first. I'm gonna have to zoom in because it's actually really small. It's this little guy right here. That's the Hall effect sensor right here. And what it does, well, there's two different kinds. This is a ratiometric one, so that it actually, I've got a little cylinder magnet right here we can pick up. So one, I don't know which end is which. I guess I should have color coded them, but one of these ends is a north magnetic field, and maybe the other one's a south magnetic field. And this can detect a north and south magnetic field, and it can detect the strength of it. So the closer you get, the larger the magnetic field would be considered, and it'll be stronger. And we can pick that up in with this Hall effect sensor. Some Hall effect sensors are just kind of digital, and they'll detect the presence of a magnetic field, whether or not it's large or small. It doesn't really care. It's just, is it there or not? This one can actually give us a little bit of information about the strength of it. So let's get some Arduino, since we're running off the Arduino here. Actually, let's look at the data sheet for it first. Let's do that first. So here's the data sheet for the Hall effect sensor we're using. It shows a couple of different form factors, some on tape, some with the legs already spread out that would fit in a breadboard. This is the way ours came. Actually, it came like this. It wasn't in tape at all. It was just separate. Some of them are mounted on a little chip already, so that you could put it in your project. But we have one like this. They're all doing the same. The sensor itself is all the same on all of these. And it gives us some different, operating parameters here. It uses 7 milliamps at 5 volts. So 5 volts is good. That's what our Arduino is going to, by default, output. It's a linear output from, basically it doesn't detect a field linearly up until it detects a strong field. There's a temperature range, a pretty wide range of temperatures that it'll operate in. And it's going to give us, some more parameters that we might be interested in. Let's see, this should give us a graph here. Well, it's just a straight line, but it should give us a graph at some point. Yeah, here we go. We have one like this. So it kind of shows us the output voltage going from 0.5 to 4.5 volts over a range, a magnetic Gauss range of negative 400 to 400 Gauss. And you kind of see it's a linear over that range. So that's good. Here's the package if you ever needed to design physical elements around one of these. They give you all the dimensions for it. I don't know if they actually show you a circuit. Basically, it has 3 legs on it, and you hook 2 of them to power and ground, and the third one is your analog signal out of the sensor. So it will, this particular one will output an analog signal that we can use analog read to measure. Here's just showing how it's on the reel and all kinds of things like that. I don't know if there's anything particularly interesting. Looks like we can get CAD models of these already made if we wanted to. I didn't bother to download that, images, all that kind of stuff, installation instructions, all that kind of stuff. So this is the type of thing that will be in a data sheet. All right, now let's look at Arduino. Here, I've already written the code. There's hardly anything to it. Basically, we initialize a variable for the sensor pin that we want to use. If we look at ours, oops, get all this stuff out of the way. I have got, oh, it's kind of, let's see if we can get it all on there. There we go, kind of. There we go. So I've got this pin right here going over to analog 0, and then I've got positive 5 volts and ground, and that's all I need. You see some circuits for this thing where there's a little capacitor in there. It's okay to, for what we're doing, it's okay to not have the capacitor in there. We just power, ground, and our signal out. So it's a super simple circuit to build, and the code is not very complicated either. I've got basically a variable set up to read on analog 0. I just have a value set as 0 as the initial value. If you wanted to store it, we don't even really need that, but that initializes the variable. I am going to print it out to the serial monitor, so we're not actually using the SD card or anything to store it. We're just going to print it out to the serial monitor. And then in our loop, basically we take a reading off of our pin 0. Then we print, and I'd use print line so that it'll go down to a new line every time it gives us a new data reading. And it's going to print that value we just read. So again, that's going to be a number from 0 to 1023. And those correspond to how many volts the Arduino is sensing on pin analog 0. Then I give it a 100 millisecond delay, and it does it all over, or it does the loop over again. So if we run this, oh, well, if we plug it in and run it, there's the plug in, let's upload it, and let's get our serial monitor so we can see it. I'll see if I can get it on the screen. Let's see, where's it at? There it is. All right, so we're putting out 500. Remember, if we're right in the center, 2.5 volts, if we're reading 2.5 volts, then it should be right around 512, which I see some 512, some 510s, 511s popping out. So basically, it's not detecting any magnetic field right now. But then if we bring our magnet closer, let's see, oh, you can already see it went up to 527. So it can see that there's a magnet that far away, and the closer I get, the larger those numbers will appear until I eventually max it out. I don't think it'll go all the way to 1023 because, well, it goes to 1001. Remember, our data sheet said that it maxes out at 4.5 volts. So that's, I assume, if I calculated it, that 1001 would correspond to 4.5 volts, or close to it. It may be offset a little bit. And if I turn the magnet around, now I should drive the numbers lower. See, I get close to it, and the numbers drop a little bit, and then eventually they may go all the way to 0. Yeah, there was a 0 if it gets really close. And so you can kind of, within a range, you know, it's not super close. Let's see, it can pick it up from, looks like that's about an inch, a little over an inch away. It can detect that something's there. And then, you know, ½ inch or so, it could definitely detect that something's there. So that's Hall effect sensor. That's a ratiometric one or a linear one. And it will detect the presence of a magnetic field, and it can even distinguish between north fields and south fields. So it's really easy to use. You can use these in like an encoder, a wheel encoder, where the magnet is on a wheel, and every time it goes around past the sensor, you can pick up that it's past the sensor, and you can get a speed off of that. You know, how fast is the wheel turning? You can turn that into a distance. Maybe it's, you know, if the wheel is turning because it's traveling along a path or whatever. So you can use a lot of different things for it. You could just detect a level. You know, the magnet could be attached to a float in water, and as it goes up and down, then it could go past one or even an array of these Hall effect sensors, and as it goes past them, you can detect its position. A lot of different things you can do with these, and they're really simple and they're really cheap. All right, let's close this down. That's probably all we need for the Hall effect sensor. You do have one in your kit, so you can build, and you have the magnet. You have the magnet and the Hall effect sensor, and there's just like 2 wires, well, 3 wires, I guess, because there's a positive, a negative, and a signal wire. And it's simple to build. All right, get that out of the way. And now let's go. I'm going to close down the Arduino IDE. Let's see. Let's go to Mathcad, because that's kind of the last thing we did, where we were talking about this idea that there's some range of uncertainty around measurements that we make, and therefore when we use those measurements in calculations to produce new, secondary type measurements, then we don't really know the uncertainty associated with that. We need a way to do that. And we talked about the Klein-McClintock. So Klein, well, I think it's Klein and McClintock is all the way I've ever seen it. And that equation let us calculate the uncertainty in some kind of measurement, usually an equation where you've got several measurements combined together, maybe you're multiplying them or whatever, and it equaled the square root, and we took the summation of all of the individual uncertainties times the partial derivative with respect to maybe xi. We'll put x in there. We had to square that so that we didn't cancel out. Some of them uncertainties would be negative, some of them would be positive, and if we add them up together, they would cancel out. So we squared it, took the square root, and so we did a root sum square, so that's RSS, to figure out this uncertainty in the calculated measurement. So we measured a bunch of individual measurements, used those to calculate a new thing, and we figured out the uncertainty in that calculated measurement. So let's do that in Mathcad. So the example I'm going to use is you have a beam, or not a beam, a column, because it could be like a beam, but we're going to call it a column, and it is in compression. So it's connected, somewhere. I don't want to really bend this, but if we put a column in compression, it'll buckle, and there's Euler's equation for buckling of cylinder columns. That's what we're going to assume this is, and it says the critical load for buckling equals the 4 here is from the end conditions, so it could be mounted in a way that's not clamped. They could be clamped, they could be hinged, they could slide, all kinds of different things. I guess they couldn't slide too much because then they would not buckle. But there's different end conditions. That 4 comes from the fact that we are clamping both of these ends. So the 4 pi squared E I over L squared. So pi is pi. E is the modulus of elasticity of our material. So the material of the column. I is the moment of inertia. So these are all statics type form things that if you don't know them, that's okay. They're not really important to the Klein-McClintock process. They're important to the column buckling. And so the moment of inertia has to do with the cross section. We'll get to that. L would be the length of the beam or the column that's buckling. In fact, I might need to get a new pen. I is the, like I said, the moment of inertia of the cross section. This beam, is a rectangular cross section. The one that I'm going to use in my example here is a square. I don't have a square column here anywhere. The reason I want to do a square one is so that I only have one new variable in here, and it is B. So that B would be the side, the length of one side of the beam column. So if we had a square column, this is its cross section, and each side would be B. If I had a rectangular one, I'd have to have a B and an H or something like that. And I didn't want another variable in here. So we just have B. What we want to do with this is that if we took a column, buckled it, and measured the force that it took to buckle it, and we measured the column itself so that we knew I, we basically measured this width B and height B, so B and B, and we measured the length of it, then we could back out the modulus of elasticity. So this is a way, maybe not the best way, but a way to calculate modulus of elasticity of the material that the beam is made out of. I keep calling it a beam. It's really a column. Beams operate a little bit differently. So column, we could calculate the modulus of elasticity of that material. So again, that wouldn't be the actual way you would go about finding the modulus of elasticity, but it could work. So that's our idea. So let's go over to Mathcad. I know I already, here it is. Whoops. And I've already put these equations in the Mathcad. So there's the equation that we wrote for, I called it P critical when I wrote it down. I just called it P over here. There's the moment of inertia. This is P critical with basically B to the 4th over 12 put in for I. So that's all it is. There's B to the 4th over 12. And then this is solving for E, solving this equation for E. So nothing super fancy. We'll zoom in and make it larger. Let's say that we used our tool, whatever, I guess a ruler of some kind, and then some kind of load cell to measure the length, the size. So this is a 2-inch by 2-inch cross section for our column, 12 inches long. So it actually may not fall into the slender column if it's only 12 inches, but it has a cross section 2 by 2. That's for the static side of that. It doesn't really affect the Klein-McClintock calculation, but we might be in a situation where this beam actually isn't a slender column, but that doesn't matter. We could always change this number to something else. We could make it 12 feet and it'd be fine. And then here's the force. It says it took 564,000 pounds. So again, probably not a column in buckling. This is probably a column that's crushing. So that kind of negates this equation even working in the first place. But again, we could change this to any number we wanted to. These are the numbers we measured. Let's say that we have a 5% error on each one of these measurements. Remember, that was one of the key things, is that each measurement that was part of this calculation needed to be measured to the same uncertainty. So 95% or 5% uncertainty is pretty common, and so we're putting 5% in here. I highlighted it yellow because we'll come back and change it to what if we had better tools and there was only a 1% uncertainty. We'll see what the effect is. So this is calculating the uncertainty in each one. Basically, the uncertainty in the length is the length 12 inches times this 5%, so it's 0.6 inches. And so forth for the uncertainty in the width measurement and the uncertainty in the force measurement. So each one of these is the plus or minus that goes with 12, 2, and 564, based on the tool itself measuring that parameter. Here it is in the Klein-McClintock form in Mathcad. So I've got square root. I've got UL, so that's the uncertainty in the length measurement, so it's 0.6 inches. And then I take the derivative of this equation. Remember, we're trying to solve for E, so we want the uncertainty in the measurement E. I guess I never did calculate E. We could do that. E is going to equal this, the nominal value. And let's put it in KSI since there are other units. So there's the nominal value for E. So that's a little bit low, but that's okay. We don't know what this material is. It's an unknown material and made up numbers. We could change any of them. All right. Actually, that's KSI. Okay, 1.5 times 10 to the third KSI. So that's actually kind of high. All right. So here, there's the E. So we did the derivative of the equation E, since we want the uncertainty in E, with respect to L. Multiplied that times the uncertainty in L. And so I just let Mathcad do this derivative and multiply it times UL, and basically that comes out to be this term. Or did it put them in the same order? It may not have put them in the same order. Yeah, no, that's not the right term. It would be... I'd have to figure out which one it actually lines up with. Anyway, then we did same thing with respect to B, multiplied by the uncertainty in B, and then the same thing with respect to P times the uncertainty in P. You have to square each one of, oh, that's why these numbers look weird, because they're squared also. That I knew something didn't seem quite. This is the one with respect to B, I can tell that, because it's got B to the 10th down there. And then, let's see, these are both P squared. Oh yeah, you can just see which one is multiplied by, uncertainty in P, uncertainty in L. So it did put them in different orders for some reason. Not sure why it flipped those two, but it doesn't really matter. They still get summed together. And this would tell us that the uncertainty in the calculate in this measurement, so when we calculate just based on the plugging in the measured numbers, E, we get this value for, let's change it to this format. There we go. Actually, let's put it in PSI. Oh, wow. What I typed. There we go. So we get 1.5 million PSI, so, and that is kind of a low modulus of elasticity. For instance, steel would be somewhere around 30 million PSI. Aluminum would be around 11 or 12 million PSI. So 1.5 million PSI is really pretty low. But again, these numbers are made up. They're not an actual experiment. So if I calculate this number for the nominal value, I have to add or subtract, and let's put this in the same units. Have to add or subtract, 350,000 PSI to this, based on each one of these measurements had a 5% error in it. But I couldn't just add 5%. If I just did a 5% error here, let's see, E times error equals, well, I didn't define error until later. Let's move it down. Put it in PSI. So if I just did 5% error on the calculated value of E, I'd only have a uncertainty of 77,000 PSI, but the actual uncertainty, because I've had to combine these numbers together, some of them were squared. L is squared, B is to the 4th power, so that compounds that uncertainty in those measurements. And I actually have an uncertainty of 353,000 PSI. Now, if my tools were better and I only had a 1% error, now I've got 15,000 if I just did 1% of E, but the actual uncertainty is much lower than it was before, but it's still not just as straightforward as multiplying E times 1%. It's still 71,000 PSI on the same nominal value for E. So I just wanted to show you that so you can kind of see it in action and how you might arrange it in Mathcad. If you wanted to put one of these in, Mathcad is nice because it takes care of the units. Python can do units. There's a library for doing units. To me, it's a little bit cumbersome. It was certainly compared to what Mathcad does. Like if I wanted to say that wasn't 12 inches, that was actually 12 feet. Oh, that's the reason why. And then I get something that's actually a reasonable value for, actually that's kind of high, 222 million PSI. That's a really, I don't know if there's probably some materials that are that high for modulus of elasticity, but you know, I could easily change everything in Mathcad unit-wise, and it can track all of that. So I do like using Mathcad. You may not, I didn't go through, notice I've got different equal signs. These are the symbolic equal signs, so that it's not trying to calculate things. I'm just putting equations in. I've got definitions here where I'm defining values for variables or assignment. Here's another symbolic, here's another assignment one. So you do have to have a little background knowledge to know when to do what particular thing. But I do like how you can, you know, put it in and it looks like you would write it down on paper, sort of. You know, maybe you wouldn't write the derivative exactly like this, but it'd be similar to that. And so I do like how it handles this sort of problem. If you did want to do this in Python, so let's get Python going. There is a way. I'm not going to show the units on how to use the units, but we can get Python to do the partial derivative. So let me get Python on the screen. So to get Python to do the partial derivative, I'm going to need, I know I'm going to need math, so let's import math. And then I think I'm also going to need Numpy. And a lot of times when we do Numpy, we do it as NP so that we don't have to write Numpy every time. If you wanted to use units, there's a PINT. I'm not going to do it, but not point. Pint. I don't know if they say it pint or pint, but because I don't know what it's actually standing for. But this is the library that will help us with units. We're not going to do units in this problem. We're going to do it with a just an equation that's not built for units. All right. And then what I've got to do is I need to, first of all, when you're doing finite difference, the idea is that you are taking really tiny steps. So you're calculating an equation and moving over a tiny amount and calculating it again and basically calculating the rise over run over that step. So, you know, you can get a slope because that's what we want. We want a slope at this point in order to, that's going to be the derivative. And so part of what I need to know is how small is the step I can take, because you can't just arbitrarily pick a number. You could, I guess, but you might pick a number that is too small, a step size that's too small, and your processor that you're using in this whatever program you're writing can't resolve numbers that small. So one thing you need to know is what's the smallest, it's called the machine epsilon. So what's that value for your machine that you're using? So in Python, how you can do that is, assuming you have the Numpy library, which we do, we can print out so that we can see it. Numpy, here's a f-info, and we want a float number, and we want the machine epsilon value. So this will give us the smallest step size that our machine can calculate. So if we run this, oh, well, if we save this, then run it, let's see, this is going to be partial derivative. All right. There it is down there. This 2.2, all these decimals times 10 to the negative 16th. That's the smallest step size that my machine can actually resolve. So that'll tell me the number, the size of the step that I can take. We need to define a function, or well, this is one way to do it. We're going to define a function to actually take the derivative of. Well, doesn't matter what we call it, but let's at least spell my function right. My function is going to take a list of parameters called x. So x could be one number, or it could be a list of a whole bunch of numbers. In this case, it's going to be three things. We're going to have coefficients of a, and a is going to be the first number that we put in for x. B will be the second number, and so forth. And c will be the last number. So x is a list that has three numbers in it. And then what we're going to do is we're going to return, this is the actual equation we're going to use. We'll use a squared, so that would be 2 asterisks. So a squared times b, so that's a squared b plus c. That's our equation. So if the one we would just did in Mathcad, we would have to spell out that Mathcad equation for e. I don't know if I still have it pulled up. There it is. We'd have to spell out this equation: 3 times L squared times P divided by the quantity pi squared B to the 4th. So we'd have to do that in this thing. And we'd need another one because we have, no, we only had 3 variables in there. P, L, and B were the only ones. So we could actually make this kind of work, but we'd have to redefine how it combines the numbers together. So all this does is this would actually calculate the value, the nominal value. This would calculate the nominal value if we gave this function the coefficients a, b, and c, the values for a, b, and c. In fact, why don't we set those up? So my variables, again, that they can call it whatever you want to. This is going to be the list 5, 2, 1. So this is going to be a would be 5, b would be 2, and c would be 1 if I print my function and send it my variables. So 51 would be the answer to this equation, a squared b plus c, if I sent 5 for a, 2 for b, and 1 for c. So that all works, but none of that's the derivative part. That would just be the nominal value. So here are the nominal values for the variables, and 51 is the nominal value for the equation. Now we're not going to actually do the Klein-McClintock part because then it starts getting longer and longer. We're just going to do how do you even get the Python to calculate the derivative. So here we need we're going to create a function for a complex derivative, or well, complex finite difference. So we'll call it Diff. And it's going to take 3 things. Well, it's actually going to take 2, and then the third one is optional. It's going to take f. So f is going to be the function that we want to take the partial derivative of. All the variables x, so this doesn't matter that I used x here and I'm using x here. That's not the point. It's whatever I put in this spot when I send the parameters to the complex diff function, and I'm going to put the variables in that spot right there. So this x is going to become 5, 2, and 1, just like it did up here, but it's not because it's called x. It's because it's in this spot. So we'll look at that again in a minute. And then we need the step size, which we're going to define by default to be info, that machine epsilon value. All right, so remember you can define some of these as optional. You can send it a new value, or you can say, hey, h is the 3rd parameter, and if I don't send anything, then it's going to equal this machine epsilon value, which is the really tiny number down here, the 2.2 times 10 to the negative 16th. All right, now the function is going to need an empty data frame. So this is just an empty list, and this is, hopefully we can get through this without too much complications. So for I and E, so there's two iteration variables, I and E, in enumerate X. So I don't know if we've used enumerate X before, but what that does is, remember, X is whatever we sent here, which is going to be this eventually. I haven't done it yet, but it will be that. And so there's 3 things in the list X here, and so it's basically going to enumerate 3. There's 3 things in there. So it's basically counting however many things there are in that list. That's how many times we're going to go through I and E as iteration variables. Hopefully that makes a little bit of sense, but it takes a little while to get these things straight in your head on what all these different things do. Here, CX is a variable name CX is copy X. So X is whatever we put in here, which is whatever we put here, which is going to be this once we call the function. And this is basically making a copy of this list. So we could do something like CX equals X, but then they get tied together, and if you change one, it changes both of them. And this, what X.copy means, is it creates an entirely new list, then they're independent. And so if I can change one of them, I can go in and change CX, and it doesn't affect X in any way, which I don't want it to. So we're doing the copy command. I don't think we've used that before. So all that does is it creates a copy of whatever is in X, which is going to be this list of coefficients. All right. And we could print it out if we wanted to, just to confirm that. A lot of times when I'm trying to code these things and figure out if I'm making mistakes or whatever, I would do, right after this, I would just print CX so that I could see what actually got stored in CX. Just so I could see. In fact, why don't we leave that in there so that you can see what got stored in CX. All right. Now I want to work on this copy of these coefficients. So CX I, remember I is one of the variables that's going to loop through 3 times because I have 3 things in this list. So we're actually building a complex partial or finite difference solver that could work on any equation. It just depends on what equation we put in for f and the parameters, the a, b, and c, or whatever the coefficients are or the variables are in this list. So it could be a different list or a different equation. So CXI, so this takes the I, so I starts at 0 the first time through the loop. So the first element in the new list that we just made, CX, and we're going to calculate on that thing. And it's going to equal E, which is the first thing in this list, 5, plus, and here's the finite difference part. So H times, now this one is a particular finite difference that uses the imaginary components. So I'm going to use 1J. So that's the imaginary component. Oh, well, I didn't need that, did I? All right. Now what I've got here is basically E is going to be 5. H is set up to be the machine epsilon value, so the smallest little number that this machine can resolve, which is the 2.2 times 10 to the negative 16th. And then I've multiplied H times the imaginary J value, and I put a 1 in there. You could, so it's the unit J, and you could put another number if you really wanted to, but there's no reason to for what we're doing. So this is the unit imaginary square root of -1 thing. So I've basically taken a tiny little step past 5. 5 is coming from here. The next time through the loop, it'll do 2, and the next time through, it'll do 1. All right. And we could print, now that we've done this, we could print CX, and we could even print the I, the one that we just worked on, so we could see what it's doing. All right. Now that I've modified this one little coefficient a little bit, I want to put in the derivative. This part isn't the derivative. This is taking one little step over, right? Sometimes you take a step over, take a step back, and do a kind of average thing. We're just going to take a step over with the imaginary component. We're going to take a step over and then divide by the step size, and that'll give us the rise, basically, which is, it'll give us the slope. So our data frame, we're going to add this to it, and we're going to add, if we put in this thing we just calculated, well, here, if we put it into our function f, so basically it'll go in to our function, and we only CX, notice I put CXI here, so it's only working on one element. Here I put CX, so it uses all 3 of the 5, 2, and 1, except in CX is actually a copy of this one, so it's going to be 5 and a little bit, 5 and an imaginary part, 2 and 1 the first time through. And I only want the imaginary component of this, so it's really only going to be the imaginary component of the result from this equation. Hopefully when I print these out, you'll kind of see what's going on. So that's the imaginary component, and I divide by h so I can see the actual slope. Remember, h is the step size. And that gets put into my data frame. And then I can return the entire data frame, which should have the partial derivatives at each location. So at each location, for each A, B, and C, the partial derivative of this equation with respect to A. Now it's not going to be the equation partial derivative, it's going to be evaluated. So the actual evaluated number that would go with the coefficient A, and then the coefficient B, and the coefficient C. So I should get 3 numbers out, 1 for each variable in my equation. I need to actually use my equation now. So let's print. I want to call the complex diff function we just wrote. Well, got to spell it the same. Complex diff function I just wrote. I'm going to send it my function, which itself is another little function, but I'm going to send it that, and I'm going to send it my variables. All right, so that my function will be sent as f, and my variables will be sent as x. And then right here, f of cx will take all those coefficients that we've built. Well, that's where we copied them. We've actually built them here. And call this function, which is up here, calculate it, take the imaginary part of it, divide by the step size, and I'll get one of the partial derivatives evaluated. And then it'll, since this is in a for loop that's enumerated over this entire list x, it'll do it 3 times because there's 3 things in the list. All right, let's run this and see if I didn't type anything wrong. I did type something wrong. Let's see. Oh, I have a parentheses here, but not one here. All right, try again. Oh, something else. Oh, you have to name things the same thing every time. I said my vars, and there it is, had em. Try again. Something else. Uh-oh. Oh, did I spell enumerate wrong? I could have done that. Let's see. Oh, yeah, I put R rate, rate. There we go. And it changed purple. All right, there we go. All right, so here, this 2.2, that's when we printed out the machine epsilon right there. 51 is when we printed out evaluating this function with the variables 5, 2, and 1 for A, B, and C. Here, 5, 2, 1, that's where I copied it the first time, so it's just an exact copy. And then the next thing I print is the value of CX0, which is calculated right here. So see how the 5 has become 5 plus that machine epsilon, but the machine epsilon is a imaginary component. Then we printed it out. And then I added that value. Well, I added that value, took the imaginary part, divided by the step size, and added that, which is 20. So if you did basically the imaginary part of this divided by h, well, no, I didn't actually, I never did actually print out f of cx. I never did print that. This is just cxi. I would need to actually print out f of cx. Why don't we do that so we can see what's happening. Print f of cx. All right, so here is f of cx, and it's 51.444 blah blah minus 15j. So it takes the imaginary part, which is just the 4.4 times 10 to the negative 15th. That's this part. It divides it by h, which is this thing. So if you take 4.4 times 10 to the negative 15th, divide by 2.2 times 10 to the negative 16th, you get 20. So, and 20 is the partial derivative of this equation with respect to A, and evaluated for the variable, or for the values 5, 2, and 1 for A, B, and C. And then it goes through the loop again, but now I is 1, so it's the second element in the list. So it's working on the 2, and you can see it has 2 plus the h value, and then it evaluates the equation. I get a different imaginary part, and I divide that imaginary part by the machine epsilon, and I get 25 apparently. And then it does it again for the 1, the third element in the list. So this complex diff function we wrote will take the partial derivatives of whatever function you put in f, and then x will be the variables that are in that function. So in this case, they're just a, b, and c. In our Mathcad equation, they would be p, l, and b. So we could actually make it do this equation. Now what it's going to give us is the evaluation for the partial derivative for each term. You would still need to multiply this number times the, this would be the partial derivative with respect to a. So you would need to multiply this number times the uncertainty in a, square that, and then do that for b and c, and then take the square root of that sum. So there's still a couple of more steps to actually make this do the entire Klein-McClintock process, but it would be relatively simple. Maybe if there's a bunch of questions about it, we'll come back and do that later. But I think for now, that's probably enough. It's going to take you a little bit to work through this. How I worked through making sure this worked correctly was, well, first of all, printing at every stage. So print the thing you just calculated and make sure you understand where it's coming from. And since this is not that many, there's only 3 elements, so it only goes through this loop 3 times, then write it out by hand so that you can see where everything is coming from. You have to have a little bit of understanding of what the finite difference method is doing in the first place. And this one's a little weird because it is using the imaginary components, which if you haven't done anything with finite difference, maybe you haven't done a numerical methods class yet, then it might just kind of not make sense at all. But basically what you're trying to do is take tiny little steps, and so this would be a tiny little step, right? And then you divide it by the step size, and that gives you the rate that it's changing, which is the slope. So maybe it makes enough sense that you can follow what's going on here. That's why I did show you this same thing in Mathcad, where it's, basically in Mathcad, we just did this part, is all that we wrote in Python. Is just that part, and, well, can't get it to highlight what I want it to highlight, but you know what I mean, that part. So we did the 3 derivatives. We'd still need to multiply by the uncertainties, square all those terms, add them up, take the square root to get the uncertainty, the Klein-McClintock uncertainty. Okay, let's see what time it is. Let's take and get rid of all of this stuff. We don't need Mathcad right now. Don't think we need Python right now. Don't necessarily need to look at the schedule right now. Let's do the population parameter estimation. So let's get a new sheet. I might need a new marker. This one was not doing too well, but we'll try. Population parameter estimation. So what we're talking about here is population, meaning that we have an entire we have all the data for some population, but estimation means we don't actually have the whole population. We need to estimate things about the population based on a sample that we took. And we might take a small sample or we might take a large sample, and it works a little bit differently depending on if we took a small or large sample. So there's not a cutoff point where it becomes a small or large sample, but in general, somewhere around 35 or 40 samples can usually be a large sample. But a lot of times you can't do that many samples. Like for instance, if you're doing, my PhD work was in analysis of femur fractures. I can't go get 40 fractured femurs, not very easily anyway. I can get 4, maybe 4, 3. And so how do I make any kind of statement when I only took 3 samples? And what you do is you make your statement, but then you put it inside this confidence interval. I'm pretty sure that the bone density is 50% plus or minus 10%, something like that. So that's what we're going to do now, is we're going to do kind of the same thing with uncertainty, but now we're going to talk about, we took a bunch of samples or a few samples, and what do they tell us? How certain are we that they tell us about the population? All right, so let's do the large sample first. So this is somewhere you've got 35, 40 or more samples, and we're going to say that this is a large sample. What you would say, is that the population mean is equal to your sample mean plus or minus some delta. So some parts on either side, and delta is going to be the same on both the positive and negative side. Another way you might see this written is that your sample mean minus delta is smaller than the actual population mean, which is smaller than your sample mean plus delta. Sometimes you'll see it written out that way. That's the same equation, just spread out. Another thing that goes with this is confidence level. And that'll be CL a lot of times. And so your confidence level is equal to the probability that what you just wrote is true, basically. X minus delta X bar plus delta. So the probability that that's true, that's your confidence level. So you want like a 95% confidence level that this is true. 95 is a common number. So we have the example here that maybe you have 11, whatever 11 is. 11 is the thing you're measuring. 11 plus or minus 5, you could say that with confidence level equal to 95%. But if I want to make this tighter, 11 plus or minus 3, so I'm more narrow now. This range is smaller. So now I've got with a confidence level of maybe, and these numbers are made up, right? So we'll get some real numbers in a minute. 60%. I had to drop my confidence because I made a tighter, a more difficult statement. So, I made it where this range is smaller, so I'm not as confident anymore. If I made this range larger, plus or minus 7, then maybe I'm at 98% confidence or something. All right. Let's do an example with this. Oh, well, let's remember, since we're using, now, most things, when you actually measure them, are not normally distributed. There's some factors that are shifting them one way or another. But when you only take little samples at a time, even 30 at a time of a population that has millions of items in it, then when you take those little samples, all of those little groups of samples you took, they look normally distributed. So that's why a lot of times we think of things looking like their normal distribution around a mean, when the thing you're actually measuring probably is skewed one way or another. All right. So all that to say, we can use a normal distribution where we have the Z-score. We can use that even though the thing that we're actually measuring might be skewed a little bit. We did an assignment a little while ago, or well, we didn't show it on here, but with the lottery picks, and the numbers themselves are not, they're more or less uniform. You have an equal chance of there being a 0 as the 9 or a 3 or a 4 or 5, and so it's not normally distributed. But every time we take a sample, that sample mean is going to be normally distributed. So we can still use our Z-score to get some information. So Z equals X bar minus mu over sigma. Now, the sigma is the population standard deviation, which we probably don't know. So we'll have to say approximately equal to X bar minus the population mean. So sample mean minus population mean, and then approximately our sample standard deviation divided by the square root of our number of samples. So we have to change up our equation a little bit because we don't actually know the population standard deviation. I keep seeing like all the viewers drop out and come back. I don't know if YouTube's having trouble or not. Hopefully my end is still working though. So I don't know. It doesn't say that I'm not working over here. We'll see. Looks like there were some network problems, but hopefully we're still going. So we used this once or twice maybe, and this was the Z-score with the tables of all the little numbers, and the Z was on the outside. We'll get to that back in a second. I just needed to get this right here for reminding us how to calculate Z and how to calculate Z if we don't actually know the population standard deviation. We only know the sample standard deviation. All right. One other thing with this. So this confidence level or uncertainty in our measurement is going to equal, remember we had this guy right here, the actual, this is a mu, not a u. I said uncertainty thinking it was u, but that's actually a mu. So let's make it more of a mu. That's the actual population average. Population mean equals your sample mean plus or minus Z at alpha over 2. So you have to decide what your alpha is, your level of significance, which if you remember, we just talked about confidence level over here. Alpha would be confidence level is 1 minus alpha. So alpha is the other side of it. If you're 95% confidence, then your level of significance alpha is 5%. And this is alpha over 2. So we're only looking at half of the Z chart. Times your sample standard deviation over your square root of n, which is standing in for your population standard deviation. All right, so I can use this to find a Z value, and then I can, I can find a Z value standard deviation. Basically, this is this right here. All right, so let's get some numbers in there so that it starts to make more sense. Let's say that we have a whole batch of resistors, and you know they have that little tolerance band on them. So sometimes there's no tolerance band, sometimes there's a gold one, sometimes there's I think a silver one. And each one of those means that that resistor was made within some confidence interval that it was actually a 220 ohm resistor, but it might be a 222 ohm resistor or a 219 ohm resistor. You know, there's some range in there. Let's say that we took 36 readings. So N equals 36. And the average resistance of this sample, X bar, so that's the average of all these 36 readings, is 25 ohms. So I don't know why 25. It could be any number. So if you haven't noticed, there are common values for resistors, and then there are not so common values. So you can usually create some of these resistors or buy special ones, but a lot of times resistors come in certain values, and I don't know that 25 is one of those values or not. And our sample standard deviation, S, is going to equal 0.5 ohms. So there's our, we randomly picked out 36 resistors, hooked them up to our multimeter, and wrote all that down. We're not going to write all that down, but when we wrote it down, we found out the average of all those measurements was 25 with a standard deviation of 0.5. So all of those are things we could calculate, assuming we had 36 actual data points. we're going to find, so given this, we're going to find the 90% confidence interval. Of the population mean. So mu, that's the population mean. So basically we want to know what's the range for around the population mean that we can be confident in. So this is the confidence level. We might write CL equals 90%. And we have 36, so that's in the larger, you might be on the small end of larger, but that's larger. When we're thinking of sample sizes that are small, we're in the, tens or less. So there's this gray area between like 10 and 30 that, I don't know, it might be small or large. But 30, 36, we can usually count that as large. All right, so we're going to use this right here. But first, we need a value to put in for Z alpha. Z alpha over 2, actually. So remember, alpha is going to be 10%, because these two add to 100%. And then alpha over 2 obviously will be 5%. All right. So we need to go to a chart. Let me get one on our screen here. Oh, not that one. That one. There we go. So here's a piece of the Z table. And we're using it backwards, remember. We're trying to get 5%. So, oh, no, we're not trying to get 5%. We're trying to, this one, remember, let's go off of this for a second. Get them all off of there. This chart, it doesn't show a picture of it here. But this chart, I believe, is giving us this value. This 5% is actually this little piece over here. So we actually, in the chart, are looking for the one that corresponds to 45%. All right, now let's go back to the chart, now that we have an idea what we've been looking for. There it is. Unfortunately, there is not a 45%. There's a 44.95% and a 45.05%. So we need the number between there. So the 44.95 goes with 1.64, and the 45.05 goes with 1.65. So right in between those would be, right in this gap, would be where the 0.45% or the 45%, 0.45 decimal, it would exist. So we need to interpolate between those two. Now in this case, they're actually, this one is 5 10,000ths below, and this is 5 10,000ths over. So it's directly in the middle. So we don't even really have to write anything down. We can just write Z alpha over 2 equals 1.645. So I just took the midpoint between 04 and 05, which would be 045. Keep pushing the wrong buttons. 1.645. If they weren't, right in the center, then you would need to go in and actually interpolate between those. But now we have our Z alpha over 2 number. And we have our sample standard deviation. We have our number of samples. We can plug in here, and we have X bar. We can plug in here and get all our numbers, right? So let's do that. X bar, so the mean, the population mean, equals X bar, which is 25 ohms, plus and minus Z alpha over 2, which is 1.645, standard deviation, oh, we're kind of off the bottom, times the standard deviation, which is 0.5 ohms, divided by the square root of n. We made a nice 36 here, so that will make it easy to do 6. If we do this math, so equals 25 ohms plus or minus, let's see, 1.645 times 0.5 divided by 6, 0.137. And then there's an ohms there, so the units would be ohms. And that, we can say, based on our 36 samples we took and got this standard deviation, we could say that, well, for the population, the entire population of resistors for these 25 ohm resistors at this factory, the average is 25 ohms plus or minus 0.137 ohms. So we would know that that batch could fall into whatever range. That should be the tightest tolerance that they have, because that's, yeah, 25 times, I think it'd have to be over 1 1/4 ohms for it to be outside of the 5% tolerance. So, and we could say this with 90% confidence. So if we wanted to be 95% sure, then what would change is we would go get another, we would get another number from here. Alpha over 2 would be 2.5, which would mean we'd have to have 47.5 in our chart, which would change this number for Z and this, and it would get larger. And so this would get a little bit larger because we want to be more confident that we're correct. So in order to be more confident, we have to open up this range a little bit. All right, so hopefully that makes sense. What if we didn't have 36 samples? So if we don't have, it's not large, it's less than 30, or it's significantly less than 30, but 30, 35, somewhere in there, and I don't know if you'll ever find a exact number, 30 or 35, some people will say 40. I think what we're using in this course is 30. 30s are cut off for large and small. So if it's not 30 or more, or if it's not 31 or more, then what that means is that kind of the same things are true, but we have to approximate the idea that our sample is normally distributed. And when we have to approximate a normal distribution, we use the t-test, or the student distribution. We did that. Well, we didn't do a lot with that, but we did talk about it. So for it, we had this equation for Z. There's a similar one for T. It actually looks identical, except it says T. T equals sample mean minus population mean over sample standard deviation divided by square root of the number of samples. That's the exact same thing as we had for Z. The difference is going to show up in our chart that we use. We're going to use the T distribution, not the Z distribution. We'll have the exact same equation, or a very parallel equation here for small samples. Population mean is going to equal your sample mean plus or minus, instead of Z, we have T alpha over 2 times the sample standard deviation divided by the square root of the number of samples. Make sure that stays on the page. All right, so here's a different sample. This time we have 1, 2, 3, 4, 5. We have 6 samples. So definitely did not take a large sample. We have 6 samples. These are DVD system time to failure. So we don't have time to test a whole bunch of these, and they're more expensive than a little resistor. So we only did 6 of them. And we want a 95% confidence level. So a little more. Last time we did 90% confidence level. So we're going to do 95% confidence level this time. So that's going to also mean that we have a larger plus or minus just because we want to be more certain that we're correct. We did 6 measurements on mean time, or time to failure, I guess. Not mean time to failure yet. We'll do that in a second. We have one machine that failed at 1,250 hours. These are hours. 1,320, 1,542, 1,464, 1,275, and 1,383. So those are our average, or well, the time that these 6 different machines took to fail. These are all in hours. So X bar, we literally go in and add them up, divide by 6. Hopefully I typed all those right. 1372.3. Yes, all right. And we want to say that, well, we only sampled 6 of these. We're going to sell 5 million, hopefully. What can we say about the 5 million based on these 6? First of all, that's probably, that wouldn't necessarily be a good thing to do, because you probably take a significant amount of time, more than one day, to make 5 million of these, and we only sampled ones from one day. Maybe these were from 6 different days. I don't know. There's a lot that goes into the experimental design itself. Like, do you take these at random times during the day? Do you take them at the same time but on different days? How are you going to set up your test? Generally, if you're taking a small sample of a large population, you want to be as random as you can so that you don't get factors like, well, turns out the machines that are making this donut work better after they've been running for 2 hours. So if you took all your samples from that time period, then you're not getting a really broad idea of what the machine's actually doing. So you have to be conscious of parameters that are going to affect time of day. So you might have to do a whole bunch of tests to figure out what test to do. Anyway, this is what we're doing. We took these 6 samples, and we don't know what the population is either. I made up 5 million. We just want to say that if these accurately represent a population, then what is the population mean at 95% confidence? Since we only took 6 samples, we have to use the t-distribution. We do need our standard deviation, which we can calculate. Standard deviation is equal to summation of the square root of each individual measurement minus the sample mean, 1372 squared, over n minus 1. I don't think I want to write each one of those out. I know this number. I'm already looking at it right here, and it turns out that it's 113.6 hours. But basically, if we did some of them, we'd have 1250 minus the sample mean, 1372.3. And notice that's a negative number, but then this gets squared, so it becomes positive, and we divide that by n minus 1, which is 5. We had 6 samples, so 6 minus 1 is 5. So 299.1. And then we would add on the 1320 minus 1372 squared divided by 5, and keep all of those. Well, actually, we take the square root and add up all of those things. All right. All right. I was trying to decide if this summation was inside or outside the square root symbol, or if it matters. But we'll come. This is the standard deviation, so we'll come back to that whenever I think of it. All right. So we want a 95% confidence level, and that will mean that alpha equals 5, and we want alpha over 2. Most of the chart, or the chart that we're going to use, is going to give us an alpha over 2 number. Most of the charts are only one-sided and assume that the thing is a mirror image about that mean in the chart. So most charts aren't going to give you alpha. You usually have to look up alpha over 2 or 0.5 minus alpha over 2. So alpha over 2 equals 2.5. All right. So let's look at our t value. I guess I need to get this on the screen. Nope, not that. That. All right. So the t value, remember, it works a little bit different where we have this degrees of freedom, which is the number of samples you took. We took 6 minus 1. So we're on the line for 5. And then across the top here for the t distribution is the significant level of significance. We wanted a 2.5%. I guess I should have written these on my page as percents. Good grief, I gotta get to percent, which is 0.025 decimal. So that will match up with this column right here. So we take degrees of freedom 5, 0.025 level of significance gives us a t value, or t alpha over 2 value of 2.571. So I'm going to write that down. 2.571. All right. So I just wrote that here. Then we just fill in the equation. We know standard deviation. We know our number of samples. We found our t alpha over 2, and we have our sample mean. So the population mean is going to equal 1372.3 hours. That's our sample mean, plus or minus t alpha over 2, 2.571, times standard deviation was 113.6 hours, divided by square root of n. N is 6, so square root of 6. So that equals 1372.3 hours plus or minus, I'm running out of room, 2.571 times 113.6 divided by the square root of 6. 3,000? No, that I didn't calculate that right. So let me do that again. Oh, because I added the answer in there. Sorry. 2.571 times 113.6 divided by square root of 6. 119. That's more reasonable. So plus or minus 119.2 hours. So that would be the population mean. Or sample mean, but we have to add in basically 120 hours on either side to get a 95% confidence level if we only took these 6 samples. Now if we took more samples, notice, well, you can't notice much, but notice that if we had more samples, just one more sample, that same value for t alpha over 2 would drop a little bit. If we only had one sample, we have to multiply by 13 basically. So there is, as you take more and more samples, basically the t chart, t distribution, as you take more and more samples, is going to approximate the normal distribution. So in around 30 samples, it basically tells you the same thing that the normal distribution tells you. And so you could just consider it a large sample. But these really small sample sizes, like the one I said, if I only did 4 samples of bones and I wanted a 95% confidence interval, then I have to multiply the standard deviation by 2.8 and then divide by the number of samples, square root of number of samples, which would just be divided by 2. So, the smaller number of samples, the larger that confidence interval has to be, and the range has to be to create that confidence interval. All right, I think we've done enough things today. These are some heavier topics with the, a lot of the things you really have to sit and think about. It might even help you to draw out more of these things and really label what you're doing. Basically what we're saying is that you could create, let's say, do it from here. We have an average and we have a standard deviation. So a mean and a standard deviation, we have that. And so we could plot, you know, we could assume a normal distribution and plot it with X bar and 1, 2, 3, 1, 2, 3 standard deviations. And when we do this with the 95% confidence level and all of that, we're saying that if we do 95% confidence that there's some range of numbers around this mean that we are 95% sure that the actual population mean is in that range somewhere. So if this is our range, you know, this is the X bar minus delta, and this number is X bar plus delta, that we're 95% sure that the actual population mean, you know, it represents its own population. It falls in that range somewhere. We don't know exactly where, but it's in that range somewhere. That's what we're doing. All right, I think we'll call it quits for today. We looked at the Hall effect sensor. It's super easy to implement, and it gives you, it does give you a measurement of the magnetic field. I don't know if I would use it to measure a magnetic field, more the relative strength, that there is a field there or not there, and it's stronger or weaker. But I don't know how there are equations on that data sheet that you can calculate the number of Gauss. You know, that it gave us a little linear line from negative 400 to 400 Gauss. So you could actually calculate the strength of the magnetic field. I think it would be more useful just to have like a relative strength or the presence of a magnetic field. But technically it can calculate the strength of the field too. So you could use it for, I don't know, measuring the strength of magnets or something if you wanted to create a project around that. Next time we're going to do some more uncertainty, and we're going to talk about basically all the things that we've been sampling with our Arduino. So, you know, with the Hall effect sensor or whatever, they've been pretty slow signals. But if I'm trying to detect something that's actually kind of fast, like a sound, and then there's a pulse there that is pretty quick, then I have to be careful, because I can set up maybe a microphone or whatever, capture the signal and analyze it, and I could get a completely different thing from what the actual signal is if my sampling rate's not correct. And these little Arduinos, they don't have a super high sampling rate to begin with, so there's some signals I just can't detect with certain equipment, or I have to be careful. And we'll talk about that next time also with sampling rate. And I think we will hook up a microphone and see if we can pick up some, at least, sound. Maybe we can't pick up the note that's being played, but the presence of a note or not. All right, I will see y'all next time, and we'll talk about sampling rate.